Okay, gentlemen, thank you for coming. Again, I'm Lee Hoyt. I'm from Nebraska, McCook, Nebraska, the home office there. Jay, he's from Rapid City, South Dakota, where our manufacturing plant is there in South Dakota. That manufactures all the fertilizer that comes up here to you guys. Appreciate you coming. Had a talk to a guy the other day at the coffee shop, and he is a guy that was hitchhiking, and he said, you know Aaron? I said, the big Aaron you mean? He said, yeah. He said, you know, he said, I was hitchhiking the other day, and he says, driving along, or standing there, and pretty soon Aaron drove up, and he said he stopped and opened up the door, and he said, get in, let's go. So he said, I threw my bag in the back. He said, I told him, he said, when I got in there, I said, you know, I'm packing a knife. And Aaron said, I don't have to. So, anyway, Aaron, we met him a couple months ago, and he invited us down to do a meeting, and we're here to show you some things. I hope you left your baggage at the door, because there's a lot of things here that we're going to show you that probably you haven't seen before, haven't heard before. Jay is a chemical engineer, and he came to us about 7 years ago and has taught me a considerable amount over the last 7 years about products and how they're made. I've been with the company for over 20 years, and you know, I knew how the products were manufactured, what they do, and how we kind of made them in general terms. But Jay brings another aspect from the chemical engineering side, and some of the things that he'll talk about is probably going to go over your head as far as how the micronutrients and different chemical makeups of our products and those types of things. But we're here to explain to you how they're made, and hopefully you understand, have a better understanding on why we ask you to use our products. We've been to a lot of meetings, and you have too, that fertilizer and seed corn and whatever meetings, canola meetings and that, and competition, other fertilizer companies, and they tell you what the fertilizers are. They tell you how much they cost. They tell you, and they show you slides on what the yield value was. And so we're going to go a little step further and try to explain to you about our products, how they're made, and how they can benefit you. So to get started here, we're a Kugler company. We're family owned. Carl Kugler started the company back in 1924. Russ come along. He owned a gas station and a zoo in the back of the old gas station in a town of about 250 people. And Russ come along and wanted to get in the fertilizer business, and so they built the first ammonium thiosulfate plant, ATS plant, west of the Mississippi. And so Russ kind of went from there. Russ's idea of building fertilizers is that two hands can do more work than one hand. And so all of the fertilizers that he developed had NPK, sulfur, and zinc. As far as starters go, get in the nitrogen grades, they had nitrogen, potassium, sulfur, and zinc. So a lot of our products are packed full of nutrients. All our products that we ship up here will be products that don't have water in them. So keep that in mind as far as when you're blending and that type of thing. And Carl's goal, as you can see there, was provide every customer with the highest quality service possible. We have plants. The main plant is in Culbertson, Nebraska. We have 20 million gallons of storage there. We have another manufacturing plant in Ulysses, Kansas that covers Kansas, southern Kansas, Oklahoma, Texas. We make ag grades and low salt starters there. We have a retail plant in Burlington, Colorado. We have another plant in Sterling, the same one as Ulysses. The Rapid City plant is a specialty plant It manufactures slow-release nitrogen, low-salt starters out of that plant. And then we're in conjunction with Hydrite Company, and they have plants in Waterloo, Iowa, and Terre Haute, Indiana. They manufacture KTS and ATS at those locations because their process of manufacturing chemicals that they made was close to the manufacturing process of ATS. So we went with them to expand our footprint a little further east. We believe also in the future of agriculture, of course. We also believe in the 4 R's, the right time and place and rate and source. And we also, I threw one in there as far as the environment goes. At home, we're under a lot of water restrictions. And I think it's just a matter of time till everybody's kind of in that deal. It may not be so much up here, but you know, as far as the Mississippi and the Gulf and so on, with all the algae and the Lake Michigan and so on, we need to be treating the environment right. We're going to have a little class today, a short course here on feeds and feeding and plant health. You probably thought that what the heck am I doing here with feeds and feeding and plant health, but let's take a look here. You don't feed the pigs on the other side of the fence, do you? Where do you feed the pigs? You feed the pigs in the trough. You don't feed the cows, your dairy cows, once a day. You feed the cows at least twice a day. Why do you do that? You do that because you want to get the most milk out of the cows, and you want to get the most weight per day on those hogs. So you've got to feed the hogs in the right place, and in-grow applications is the right place. Are you ready?
Yep. The right place is directly under the seed. We've seen relatively dramatic increases in yield when you put the fertilizer down in the seed trench, then put the seed on top of it. Think about it for a minute. Which direction do the roots emerge from that seed? Now, the other benefit of our product is that we're 80% orthophosphate. Now, why is that important? It's extremely important up here because of your cold soils. If you were in Alabama, 80-degree soil temperature, black, dark soil that's going to soak up that sunlight all day long, there's a process that involves something called hydrolysis of a polyphosphate, which the plant does not recognize as a nutrient, to orthophosphate, which the plant does recognize as a nutrient. That happens very quickly in warm soils. In that Alabama scenario, it's about an hour. Up here, it's never going to happen until your soil temperature reaches 58 degrees Fahrenheit. That's the time that polyphosphate undergoes that hydrolysis chemical reaction and turns into orthophosphate. And so if you put a high ortho product, you'll be told time and again that 1152O has high orthophosphate. Well, that's true. That granular material in your hand is about 70% orthophosphate. But the second you dissolve it in water, it abstracts a proton. It takes a hydrogen atom off and it turns it from MAP to DAP very quickly. Now all you have in there is polyphosphate, and you've got to wait for that conversion to occur. That's why we see such fast pop-ups in our product mix. Generally 2 to 3 days it starts to emerge. Now if you can pick up 2 and 3 days on the front end, you generally can pick up 5 to 7 days on the back end in terms of the time when you're going to harvest your crop. And then you can be harvesting earlier. That's a benefit of that initial high orthophosphate being immediately available to that plant rather than that polyphosphate just sitting in that seed trench. Does that make sense to everybody? Have you heard in the past that the plant only recognizes ortho as a nutrient? I'll give you another parallel. How many of you broadcast a urea source? Pretty much everybody, right, at some point. Is urea a nutrient? The answer is no. Urea is not recognized by that plant root until the bugs act on it in the soil and they turn it into a nitrate. Now, the plant recognizes it as a species that will transfer from outside of that root to the inside of that root as a nitrate. As a nitrate, is it a nutrient yet? Obviously not, or I wouldn't be asking the question. It does not. It's not yet. It's got to go through a process called nitrate reductase, which is an oxidation reduction reaction within the plant. And it's got to take that nitrate and break it down into a nitrite, NO3 to NO2, and then break that down into ultimately an ammoniacal nitrogen, an NH. Now it's a nutrient. Now it's a food source. Other than that, it's nothing other than something that's cooking in a pan. You haven't eaten it and digested it yet. And it's essentially what's happening in that plant. So orthophosphate is the only recognized nutrient because the plant says, now I can take that phos ion and I can turn it into energy. And that's the purpose of phosphorus to begin with. And that's why all of our products are very high in orthophosphate because early on that plant desperately needs energy to get up out of the ground. Why? Leaves. You get those leaves out there, you get that engine started, what's called photosynthesis. And then that process continues and creates more biomass and more energy, and the more of that orthophosphate that's available, the better off you are. I'm going to mention lots of other products or product types. And keep in mind that there's nothing wrong with 1152O. There's nothing wrong with 1034O or 1137. They're all products that have certain features and benefits. We're going to try to tell you the difference between those products and our products so that you have enough information to make a business decision. Does that make sense to everybody? These are our products. The KQXRN is a product that we incorporate into starter fertilizers because it has such a low salt index, and I'll get into why salt index is so important in a minute. The 1410-2 and the 1022 both have the KQXRN slow-release nitrogen. It's called a polymethylene urea triazone. It's a 28% nitrogen, but there's no water in it. And it's made up of 65% urea. You can't get that much urea into a water solution. We polymerize it, and each one of those polymer units that you get is 150,000 strong. And so it breaks down slowly over time, hence the concept of slow release, and slowly feeds foliar through that plant, but it also gives a benefit because the salt index is so low. If you can get the KQXRN to burn, I'd like to see it. Because I don't care how much you put on with no water, you cannot burn your leaves, even though it's made up of 65% urea. And I'll show you some pictures of what the chemical structure looks like in a little while. Our LS624, 924, 918, and 318 are all very typical low salt, high orthophosphate products. They've been around for a long time. They've been manufactured for over 50 years. It's not new technology, but it's still the only thing out there that's low salt and high ortho that's also affordable.
Guys, this is your meeting, so please ask questions as we go along.
And we also contain potassium in every one of our starter fertilizers. Potassium does impact early seed vigor as a result of stalk strength and metabolizing nitrogen in that plant. So it's very important to have available potassium. And all of our potassium doesn't come from potash. It comes from potassium hydroxide. And again, the K plus ion is the only potassium that that plant recognizes. It doesn't recognize potash. It's got to go through a microbial process, and essentially the microbes chew on the potash and they pee out the chloride ion and they pee out the potassium ion. The plant now recognizes that potassium ion immediately as a nutrient source. And of course our KS Maximum is our micronutrient package. We recommend that you use it because you get the biggest bang for your buck when you use a micronutrient package early on in the planting process. Our applications cannot by themselves meet the total nutrient demand of the crop. We are a supplement. We are not there to act as a replacement for a good quality soil program. So always start with your soil tests. Your soil tests, you need 200 pounds of nitrogen and you need 40 pounds of phos in there. Find a way to get it into the soil, because we are there as a starter by definition. We're there to get that plant up, emerged, and get the initial leaves out so that that engine gets started and photosynthesis gets going. There are competitors of ours up here in Canada and lots of them down in the States who'll tell you that 5 gallons of a 624-6 is sufficient phos for your entire season. You really do have to challenge that, because physics is physics. What you take out, you got to put back in. I mean, it's as simple as that. And if it's available, that's great. But if it's not available, if it's tied up at high pHs or low pHs, you're going to have to replace it. And 5 gallons of our starter fertilizer is not enough for that plant for the entire season. So why use a low salt starter? Less fertilizer is applied. Available in cooler soils. We talked about that a little bit earlier as far as the transition from polyphosphate to orthophosphate. Used in all kinds of soil types. The salt index is lower. Salt index is a direct function of electroconductivity in the soil. The higher your electroconductivity in the soil, as a result of high salt concentration, the higher your osmotic pressure. The higher your osmotic pressure, the less ability that newly germinated seed has to take water out of the soil. That's what salt, that's why salt is so bad in your soils. That's why when you get a high salinity soil, that white salt that's sitting, it's as a result of sitting water at times, but there's other reasons why you can't plant anything in there and have it grow. It's because the osmotic pressure is so high, because the electroconductivity is high, and that root is not able to extract soil water. That's the reason why it doesn't work. That makes sense to everybody? Okay, you can apply it in dry conditions, obviously because it's a liquid material. You get the very early seedling pop-up capability, helps to establish yield potential. Very important, it's 100% water soluble. A 1034-0 is only 70% water soluble, which means whatever's in there, regardless of the concentration of ortho versus poly, is only going to be 70% available. Now, to be fair to like a 1034 or an 1152, it will eventually convert. And it will convert to about a 50-50 over time with warm soils. And it also happens faster in high pH soils. So, again, there's nothing wrong with these products. It's just that 1034-0 and 1152-0 are not 100% water soluble, where a high ortho, low salt starter fertilizer is. Aids in stress reduction, and none of the products that we manufacture are corrosive. Just as emphasis, when soil temperature was reduced to that magic number, 58 degrees, which is 14 Celsius in that neighborhood, corn root growth decreased 5-fold, and phos uptake decreased 4-fold. Why? It's not converting in the soil at that 58 degrees. At 57, it's going to be worse. At 59, it's not quite as bad. When you get up into the 60-degree range, it's actually happening fairly quickly. But you guys don't have cold soils up here, right? I mean, when we first came up here 7 years ago and we saw you planting, it was in 4 inches of mud on top of an iceberg. And it takes a little while for that soil to heat up. if you are, again, down in Alabama, or essentially below Interstate 80 in the United States, we don't have much utility. You use anything you want because that conversion is going to take place very quickly. But up here, North Dakota, South Dakota, Montana, northern Wyoming, Idaho areas, up into the 3 prairie provinces, you've got to have something that's going to give you a benefit early on, rather than just it sitting in that seed furrow and waiting for temperature to warm up. Same thing with potassium. I said all of our starter fertilizers contain potassium, and the reason is pretty much the same thing. If it's immediately available in the K+ form, now the plant has something it can grab onto and it can utilize as a nutrient. But in cold soils, potassium chloride, potassium oxide, potassium acetate, they don't convert in very cold soils until those soils start to warm up. So, ortho versus poly. Plants consume phosphate in the ortho form. They break down over time via a process called hydrolysis. What you're doing is grabbing onto the hydrogen atom and you're pulling that hydrogen atom off of the polyphosphate and turning it into orthophosphate. Has anybody heard that before? No. Well, like Lee said, I've got a background in chemistry. I spent 26 years with Dow, and I've been in the chemical industry now a total of 38 years. The one thing I've learned in that period of time is that you can't argue with the chemistry. You can sure try. But chemistry is one of the most pure sciences out there, and physics and mathematics are utilized to measure what's going on with chemistry. And so I didn't know, like Lee said, the first thing about agriculture when I came to work for the Kugler company. In fact, I was flabbergasted that they even hired me. And I'm sure he's sorry about that now. But I had to approach it not from a farming standpoint, because I don't have a farming background. I had to approach it from a chemistry standpoint. So if I know how the products are made and I understand the biological physics of the plant, then I can figure out how and why these products work and what we can do to make other products and better products as well. And that's exactly how I approach this thing. And all of the research that I've done in the last 7 years has been in the direction of understanding how and why our products work, including herbicides and fungicides and other chemicals and chemistries that are out there. Virtually all fertilizer materials are salts. A salt is defined as a chemical reaction between an acid and a base. You know the table salt that sits on your kitchen table? On paper, it may not be how it was formed in nature, but on paper it's hydrochloric acid and sodium hydroxide. You put those two together, it's a strong acid, it's a strong base, and what you get out of it is table salt. That's the resultant. So a salt is that reaction between an acid and the base. In our case, we're looking at ammonium hydroxide, which is a weak base, and we're looking at phosphoric acid, which is a weak acid. You put those together, and you can, by controlling pH, you can make the products that we make, but they're still all salts. See, that's the key. No matter how you do it, they're all salts. How you make it low salt is to reduce the electroconductivity. So there's a test that you run. You take a 1% solution of sodium nitrate. It comes from sodium hydroxide and nitric acid. Strong base, strong acid. And you pass a current through it. Electroconductivity. What you are detecting on the other side is an amp second or a coulomb. And that number, whatever that number is defined as 100. You normalize it as 100, and then you run the test on your product and other products that are out there. And as it turns out, anything below 50 generally won't cause seed damage, even in very large concentrations. Anything above 50 has more of a propensity to cause seed damage. And so we try to make our products in the 40 range and below so that we're not causing seed damage as a result of high electroconductivity, high osmotic pressure, and then the inability of those roots to take up water from the soil.
Gentlemen, there's companies out there that have salt indexes in the 7s and 8s on their starter fertilizers. That's bogus. Jay can explain to you how they're doing that. I can't, but he can explain to you how to do it. So that's why we're telling you this information, guys, so you can know and you can make business decisions on what products to use.
Now, I've got a brochure in my briefcase. I was at a show in Manitoba a couple months ago, and as I was walking around my walkabout, because I like to see what's out there, I went to this one booth and it just stopped dead. And I looked at the sign and it said, "For sale, soluble sunlight." Guys need to think about that for a minute. Soluble sunlight. Okay, now I'm intrigued. So I started asking questions, and the poor kid that was sitting behind the counter, he's just there making a buck, and you know, I'm not gonna irritate him. You know, he made it very clear, I don't really understand what this stuff is, but you know, it's soluble sunlight. So he says, my boss will be back in a couple hours. Well, you can guarantee that I was back there in a couple hours. I went back and I told him what was going on, and he kind of looked at me sideways like, yeah, you know, because I gave him a lot of useless information. And so I went back and I got the brochure and brought it back. Well, he's laughing, and I really got to find out what this is, because you guys are getting hit with snake oil left and right. How do you know what you're buying is a worthwhile prospect for you? And so I finally went back and I asked the guy and started quizzing him and asked him how he shipped it. You know, is it in a tank truck or in a shuttle? And as it turns out, he's calling the soluble sunlight a lignosulfonate. Now, lignosulfonates have their utility in agriculture, no question about it. But he's selling it as soluble sunlight. And so I asked so many questions that finally he just asked me to leave his booth. Because it's bogus. It's crap. It's crap of crap. I mean, soluble sunlight? No wonder people don't believe us when we go talk to them about some of our products. But our products have been proven for the last 50 years or longer than that. And so again, we're going to try to give you enough information so that you can make a business decision. So just make a comparison. High salt soil concentration would be the disease. The symptoms of the disease would be high electroconductivity, which then leads to high osmotic pressure, which then leads to limited water uptake by a newly germinated seed. Again, why that crop doesn't grow well in those high salt soils that have those insoluble white salts on the surface. There's ways to mitigate that, and Luke will talk about that quite a lot here, and it's humic acid. Humic acid, depending on the level of soluble carbon, can tie those salts up forever. Because one carbon atom attaches itself to 4 things, whether it's hydrogen atoms or oxygen atoms or phosphorus atoms or whatever. But it'll tie itself up to 4 things, which means it has each atom has the capability of tying up 4 salt atoms. And there's a very high level of soluble carbon in humic acids and in fulvic acids. And so that is a way to mitigate those high salt areas, which aren't making you any money today. Might cost you a little bit of money to get in there and spread it around and to let it do its job, but within a year or a year and a half, you're going to be perfect. You'll have perfectly good soil. And that's the reasoning behind how we can limit the high electroconductivity. We could put that liquid humic acid in furrow and help to mitigate high salt concentrations in the soil furrow. These are our products, or just a representation of our products. It's not all of them. The highest one that we manufacture is our 924-3, and it's a salt index of 42. The KQXRN, which is our primary foliar product, is a salt index of 6, extremely low. Urea is the lowest of all of them. It has a salt index of 2. And there's only one test that you can run. You know, if you run a test on phosphoric acid for a salt index, it's not going to give you a very high number. Why? Phosphoric acid isn't a salt. If you do it on ammonium hydroxide, it's going to give you a low number. it's not a salt. So if you take those numbers and you average them, you're going to get a very low number, but it's not telling you anything. You know when they say in a computer, crap in, crap out? Well, that's exactly what they're doing. They're trying to make their products look good. There's only one salt index test that's worth doing, and it's an empirical test, and it gives you a comparison. That's all it does, is allows you to compare salt indexes and help to get away from that high electroconductivity in your soil. 1034O is 56. Does that mean it's a bad product? No. If you put it in conjunction with the seed, it's probably not going to cause any damage in small concentrations. But if you put 6 to 7 gallons in right directly under the seed, the propensity of causing seed damage increases with the amount that you put in. And always remember that water is your friend in these situations. The more you dilute it, the less damaging that it is. Our KS 1022 and 1410, as I said before, both of those, their nitrogen is the KQXRN. So you put something in there that has a very low salt index, and it's going to end up giving you a low salt index in your products. Those two can also foliar feed phos.
Also, your row spacing will make some difference on that
Sure.
too. Wider the row spacing, the less gallons you're going to have to put in the row. The narrower the row spacing, the more gallons you can put in the row. Okay?
You wouldn't put 28% UAN directly in contact with your seed in the seed furrow, because you're going to cause seed damage. And it's not that much higher than that 50, that magic 50 fence. And above it, you have more of a chance of causing seed damage. Now here's a unique chart that tells you what happens at high and low pHs. At a pH of 5 and below, you have available aluminum and iron, manganese as well, a little bit of zinc. It's available. All of those species are positively charged. They're going to tie phosphorus up, which is a negative charge. And they'll tie it up forever at those pHs. They're totally insoluble. Same thing at the high pH, as you approach 8 and above. Calcium is the big one that you're tying up at that pH. It's positively charged. Phosphorus is negatively charged. It's tying those phos atoms up, but your soil test tells you that you have 75 pounds of phos in the soil. Well, you might have available if you're in this pH range here, but if you're at high and low pHs, unless you change the pH of the soil, it's not going to be available. But your soil test says it's there. Maybe a reason why you're not getting the yields that you expect sometimes, if you have pH differentials. We find that further west of here, the pHs go down pretty dramatically. Further east of here, the pHs go up. And there's a smattering of all pHs everywhere, but do you realize that pH drives all soil